This, so I'm going to talk about stack processing with ISCE. This should really be like presented by like 5 or 6 people, because I think this work, it's a combined work of a lot of people, Harish, David, Simran, Yunjin, people at University of Miami. It's sort of in the contributed software part of the repository, and they actively maintain it as is needed for whatever projects they are working on. As an overview, ICE includes 2 kinds of stack processor, topStack processor and strip map processor, and I just wanted to show that they're in the contrib folder on GitHub. I just want to talk about some basic setup for using these workflows. I'm not going to go into too much details. I'm only going to talk about most common setup options. Then maybe Yunjin can actually show you on his computer what the process of setting up a run might look like. Of course, we're not going to do entire processing run today. That will take up too much time. Then I'm going to briefly mention the integration of outputs of stack processor to tools like MintPy and ISCE stamps or prep stack to stamps that's maintained by David. So the first stack processor we have is the topsStack processor. The workflow is described in great detail in this 2016 paper from Harish. The thing to note is you can think of topsApp, which we saw on day 1, as a special case of the topStack processor. topsApp is essentially topStack running a single pair. Whereas, like Harish mentioned earlier in the MintPy lecture, you only have to do the topo step once, and then you use that to do all the geometry mapping and alignment. The co-registration is done using cascade co-registration. I'm going to talk about it in the next few slides. But essentially, what happens is at the end of the co-registration process, we estimate a constant offset in slant range and a constant offset in azimuth with respect to a reference image. The azimuth, again, is done using ESD, and we use NESD as described in this paper. Oops, sorry. Can you see the slides back? Yeah. And range is done using AMCOR. The one important thing that I think Harish put in fairly early was the ability to update the stack with new scenes, so you don't have to start processing from scratch. And in this workflow, we've highlighted processing steps that are done only in overlap regions on a full burst scale. So there's a little bit of optimization there to reduce computation time and intermediate workflows. Let me just exit this 1 second. All right. So we use what we call cascading co-registration. Again, the details are in Harish's paper. The idea is, suppose you have an imagery, you can use a certain number of connections to estimate the offsets, either an azimuth and range, and then you can sort of do an S-pass of the offsets to get the relative offset with respect to the reference scene. And how many connections you throw in improves your co-registration quality. I think by default, topsApp sets up 3 connections, but it's a controllable parameter that you can set. The throwing in more connections sometimes, especially in the ESD step, might not be very beneficial because ESD depends on the coherence of the data. So as you go further and further away in time, data decorrelates. So there's probably not much to gain there. And of course, all the theory of using the full covariance for time series also applies to full covariance for co-registration estimation, because essentially we're doing S-pass for estimating this. In practice, we've seen that the few connections, 3 or 4, seem to do a very good job for co-registration. We did briefly talk about the impact of using or not using ESD and TOPS processing. So this is essentially what your data would look like on top if you did not apply ESD corrections. And if you did apply ESD corrections, the bottom is what you would see. You would not clearly see this burst artifacts. I believe the unwrapping artifact you saw in the previous example was either a frame boundary or a burst boundary. So that's why when we were talking about TopSAP, I said I usually turn on ESD for all processing, at least for my work. So that's essentially what the TopStack processor does. It's a more grander version of TopSAP. The details are on the GitHub, and there's a README file with step-by-step instructions. But in general, the workflow setup can be broken down into download all your SLCs, have your orbit files and aux files, prepare your DEM, and run stack sentinel.py, the script with like inputs pointing to where your SLCs are stored, where your DEM is stored, where your orbit auxiliary files are, what region you want to process, what workflow. I'll talk about what workflows in a little bit, and the working directory where you want all the processing intermediate files, configuration files to be dropped. So that's essentially what it takes to set up a stack. There are other options also that Stack Sentinel allows. The workflow SLC stops at generating co-registered SLCs. Then it is up to you what you want to do with it. You want to do PS analysis with it. You want to do fringe analysis with it. You want to form your own pairs. The workflow stops there. There's another workflow called interferogram, which runs up to SLC and then generates a predefined set of interferogram pairs. There's a workflow called offset, which starts from the co-registered SLC and generates amplitude cross-correlation pairs. This is mostly for the cryosphere community. And then there's a workflow called correlation, which maybe generate high-resolution correlation maps from the stacks for predefined pairs. There are options for co-registration. For example, if you're doing cryosphere-related offset workflow work, you don't really want to do NEST. There's nothing to gain by doing corrections at 1,000th of a pixel. You're mostly interested in pixel offsets. So you can just say use geometry, in which case it'll skip all the ESD steps and just use geometry to co-register your images to generate a co-register stack. You're studying a very small area. You can specify the region of interest, and you know you only want to focus your analysis on one swath. You can control that with the swath number. You can pick a reference state that's not the first state, but I think Yunjin might have more experience with this. And if you are picking interferograms as an option, you get to control the number of looks, the number of connections you're making, the filter strength, unwrapping methods, and things like that. The things to keep in mind that I think, at least as a checklist for me, is always use full paths for folder names. ISCE isn't great at handling relative paths. So for all stack processing, use full paths. There is very little error checking in these scripts, so I would not be surprised if something failed due to a setup error and you're not able to catch it till later in the process. So yeah, just be aware that this is researchy development code. And I would say learning Python, being familiar with Python would be a big plus. If you're not very familiar with Python, it may be hard to make progress with this. So think before you commit to using this. And just like Haresh said, in MintPy, everything is a standalone script. Everything is a standalone script in the stack processor as well. You can run each script one at a time. What does the Stack Sentinel PY, what does this do? This essentially creates a folder named config, which has run files and config files. A run file is basically like a series of commands that you need to run. To run it, you just say source, run file. And these are numbered from 1, 2, 3. So you do step 1, step 2 in sequence. You'll see more when Yunjun probably shares his screen. And each run file has a number of system calls or a number of calls to config files. And one config file is one processing step. It basically says run this Python program with these arguments. For example, once you've done your stack processing and you realize you want to do more interprograms, you don't need to go to the very first and rerun the entire stack. You just add more config files for your interprogram and just run that at that stage. So that's essentially Stack Sentinel.py in a nutshell. There are known limitations for this, as you are all familiar with, or you might have encountered at some point. Sentinel-1 has inconsistent frame boundaries. The framing is not consistent. So I think at this point of time, we need a bounding box to be specified. I think that's our only way of standardizing this. I could be wrong, but that's what I seem to remember. If you have multiple scenes with great varying spatial coverage on different dates, we suggest use the scene with the greatest spatial coverage as a reference scene, so that you have a reference on which to pin the smaller scenes on. Don't pick a smallest scene as a reference. There is currently no way of handling missing frames in the middle of long acquisition. For example, there are images in San Francisco and there are images in LA, and they didn't acquire images in Central Valley. You can't create a stack from San Francisco to LA with scenes with gaps in the middle. So that is one known limitation. Also, be prepared, have a lot of disk space, and have a lot of multi-core processors to be able to process all these data sets if you're doing it on your desktop or your cluster. So before moving on to StripMap, Yunjun, do you want to take over and show us what you have?
Sure.
Yep.
Okay, so this is just to show in reality how the directories of stack processor looks like. This is in a folder here for this one chunk of data set, and then I've downloaded SLCs from. It makes sense. This is easier. So I've downloaded SLCs from ISF. You can download that from the ISCE website too. I've downloaded a lot of SLCs. You can see here a huge amount. There's instructions on the downloading on the SF website. I downloaded them within this SLC folder. And then I've also just exactly followed the instruction on GitHub for the TopStack, and then prepared the DM for this dataset. And looks like this. These are the DM corrected for the geoid difference to the ellipsoid. And the orbit folder here has some orbit data, but this one we don't need to worry about it because the stack processor will download them automatically. I think this is from my last rerun previously. So now I'm just showing an example of how the stack processor looks like. If you just run Stack Sentinel with the help, you will see the options with all the options that you just described. And for us, let's just try one example in here. I have Stack Sentinel here with to specify the SLC folder, and then to specify an orbit directory, to specify an auxiliary directory, which is just some kind of calibration from ISCE data. This, you can just specify that, you can just create a directory on your system anywhere so that you can access them all the time. Specify the DEM. And then here, I'm applying looks. I'm applying, since I don't need high resolution data, so I just use relatively low resolution. This is what I'm using actually all the time, most of the time. I'm using 15 looks in a range direction, 5 looks in axis direction, and then with a number of connections. with a number of connections of 3s, and then I use, since I'm using the geometry for illustration, and since Sentinel has 3 subswats, and actually in this time I'm processing both 3 subswats, I can just processing 1 or 2, just using that, and then just processing 1 or 2. I'm processing all 3, and last I'm specifying a bounding box. And a bounding box is specified in the order of the south, north, west, and east. So in here, this is actually a region in Cascadia near Seattle. So in here, I'm specifying the bounding box here. And then just run. So there's a table here.
And Yunjun, is the preparation for the DM exactly the same as for the TOPS app?
Yes.
Okay.
Yes, it's exactly the same. So let's go through the printout message. It just basically says that there is around 200 save files that downloaded and found. Only a part of them is used by covering the bounding box. And among this much data, there is 100 dates as listed here. And then since we specified a bounding box as this, then the script will check the preliminary bounding box based on the KMZ file attached with the data. And then it finds that among the 100 dates, 92 dates fulfills the bounding box requirements. You can also see this for your reference if you want to adjust the bounding box for your processing. Since in here I did not select a reference date manually, so the first date will be used as a reference date. And now you can see that it writes all these round files as what just Piyush described. And if we check the directory again, besides the previously 3, the SSC folder is the round file folder is generated, the config folder is generated. And if we go to the round file folder, we can see exactly all these files. So if we look at each of them independently, this is just one script for the first step, and you just run from one to the last. And for example, in this one, the last one is the unwrap. And if you look at it, it just basically literally unwrap every single interference. And these are just the running script, but the configuration of every single step is set it up in the config folder. For example, in here, still let's check the phase unwrapping for this one. If you open this file will be called for the unwrapping for these pairs. You can see the inputs, the output, the coherence, and all the other detailed parameters for each step. So this is all generated when we run the Stack Sentinel. Basically, after run that, go to the run file folders and run every single one of them. After you finish all of them, then you're done for the stack processing. That's it.
And what criteria was used to make the pairs here? Was it like an N-to-N, or was it plus or minus 3 dates?
It's Piyush, you want to drop something?
Did you define that somewhere, or?
Yes, we define it in here. We find it here. This minus C, the number of connections. This is literally for each date, you make the 1 or 2 or 3 newest connection to the dates, to the acquisitions before that. So basically here, let's say here we have acquisition D, A, B, C, D, and here all the way, if we specify minus C is 3, then it forms the connection of CD, BD, and AD.
And he specified that on the command line. You go back
Yes.
to your command line.
in here, I specified it in here. You see?
Right.
Yeah. And of course, you can add more or use less. And details can all be found in the help of the scripts.
But that's the only way of defining pairs. You couldn't have one reference and then use all of the, it kind of works in this network mode. You can't have one reference file and all your other interferograms as secondary, for instance.
You can create as many, see, the config files are really simple. They're simple text files. You can easily write a script to create as many config files as you want.
Right, right. Okay, cool, thank you.
So I guess that's it.
Nice, thanks, Yunjin.
Thank you.